All right, so this is continuing the video in AP Calculus on U substitution, section 6.2. This is the second video on that topic, and we're just continuing to work some indefinite integrals where U substitution is going to be the most beneficial way to go about it. Now, this particular problem, when you first look at it, you may wonder where exactly the U substitution comes from, because what we've done in the past, in the previous problems, was we had a function inside of another type of function, and so it was easy to identify what the U was, because it was usually the inside function. Here, though, I don't have a function within another function, but I have two functions that are being multiplied together. Now, I could legitimately distribute those things and multiply them and integrate piece by piece, but let's see how we could possibly do U substitution with a problem like this. When you're choosing your U and you have something like this where you don't really see one function inside of some other type of function, your U is usually going to be the more complicated or the higher degree function. So in this case, I would suspect that my U is x squared plus 2x minus 3, which would make du 2x plus 2 dx. Now, usually this is immediately where I go look over at my integral and say, okay, do I see 2x plus 2? I don't. I see x plus 1. But if I manipulate this by factoring out a 2, now I see x plus 1 and dx. So I do not see a 2 though, so I would have to divide it over with the du. And so 1/2 du would be equivalent to the x plus 1 dx. And this guy would be equivalent to the u. So that makes my integral 1/2 u du. And you may be wondering why I tend to separate the constant that's times the du. That's just because typically we write our constants in front. So I kind of separate those two things and then stick the u stuff in between them, just because that's how we're used to writing things. Well, now 1/2 u is really easy to integrate. This is a reverse power rule problem. This is a u to the first, so it would go back to u to the second. But I do old coefficient, 1/2, divided by new exponent, or times the reciprocal of the new exponent. Don't forget my plus c. So that would be 1/4 u squared plus c, or 1/4 x squared plus 2x minus 3 squared plus c. So this is why it probably would not have been a good idea at the beginning of the problem to distribute those and integrate piece by piece, because that 1/4 x squared plus 2x minus 3 quantity squared, that would not have come about from me integrating piece by piece. I would have had an expanded form polynomial, and I would have had to figure out how to factor it to then get back to this 1/4 x squared plus 2x minus 3 squared. And so that would, number one, I probably wouldn't do a very good job of factoring it. Let's be honest, guys. And number two, that's just more time that I'm have to try to spend factoring that. So doing the U substitution route would have helped me find this answer a whole lot more quickly. All right, so let's look at another one. Here I have two functions again. I have sine to the fourth x times cosine x dx. So again, I have to decide which is my u. Is it sine of x or is it cosine of x? Well, again, you need to choose the more complicated one. Notice that sine of x is inside of that 4. This is like saying sine of x to the fourth power times cosine x dx. So the inside function there is sine of x. Now the awesome thing is that when I take the derivative of that, the derivative is cosine x dx. So there's my du. There is my u. So my integral becomes u to the fourth du. Super easy. Reverse power rule. Then substitute the u back in. And you're done. Simple as that. All right, now this next one, you may have to bear with me a little bit on this one. So I'm looking at this one, and I see that if I pull the dx out, this is 1 over x squared plus 9 dx. So I'm tempted to make u be x squared plus 9. But if I do that, du would be 2x dx. Now the 2, I can deal with the fact that the 2 was not over there in my integral, but I do not have an x, just a plain old x by itself, anywhere at all in these integrals. So this method is not going to work. So choosing x squared plus 9 as my u is not going to work because I don't have an x in that integral. So this one is a bit tricky. So I'm looking at that x squared plus 9. I'm like, where have I seen something that's got x squared plus a number in the denominator? I'm thinking, oh, so inverse tangent, the derivative of inverse tangent is 1 over 1 plus u squared du dx. But it's a 1. This is a 9. So I'm thinking this might go towards backwards to becoming inverse tangent somehow, but it's not going to as long as that's a 9 and not a 1. So then I start asking myself, well, could I turn that 9 into a 1? I could. I could turn it into a 1 if I go through and I divide. Let me change colors. Every single piece of this fraction by 1. So this becomes a 1/9 x squared over 9, and then 9 over 9, which is 1. So I got my plus 1 in there. That's what I wanted. And I really need 1 to be in the numerator also, but I can fix that really easily. I can just pull the 1/9 out separately. You could even put it in front of the integral if you want to. Now this is something I can work with, because if you go back and you look at this right here is u squared. So this right here, u squared is x squared over 9. So what does that make u? Well, u would then be the square root of that, so u would be x over 3. So then du would be the derivative of that, so it would be 1/3 dx, or 3 du is equal to dx. So that makes this integral 1/9 times 3 du times 1 over u squared plus 1. Well, if I do the 1/9 times the 3, that gives me 1/3. And 1 over u squared plus 1, that is inverse tangent of u plus b. And then all you have to do is replace the u with x over 3 that we came up with for it a few minutes ago. That one is probably one of the hardest u substitution problems because it requires recognizing inverse tangent, manipulating that 9 to turn it into a 1, which means manipulating the whole fraction, so it can get a little bit tricky. Okay? Now, that being said, I want you to pause the video and see if you can try h perhaps a little bit more successfully. Okay, so if you remembered how we tried to start g with using x squared plus 9 as u, that actually worked out successfully on this problem. So that would then make 1/2 du equal to x dx. So you could replace the x dx with, here's x dx, with 1/2 and du, and instead of x squared plus 9 being in the denominator, u was in the denominator. So the 1/2 just follows along, and then 1 over u we talked about at the beginning of u substitution, that 1 over u is the derivative of natural log. So it integrates back to natural log of the absolute value of u. We do that so that in case whatever's inside the natural log is negative, we automatically make it positive so that we can evaluate the function. And then you just go back and you replace u with x squared plus 9. But notice I took the absolute value off and just used parentheses because x squared plus 9, it doesn't matter what number I substitute in for x, that's always going to be positive. So the absolute value bars would have been redundant. You can leave them on there if you want. You're not wrong if you leave them. Just in this particular problem, they weren't necessary in the end. Okay, so that covers indefinite integrals. Now we're going to look at definite integrals with u substitution. And they're not any harder, they're just a little bit different because of
the boundaries that are on them. So I'm just going to jump right into example 4, problem A, and go from there. So I'm going to start it the same way I've been doing all the others. I think my inside function there is y plus 1. So u is going to be y plus 1, which makes du 1 dy. So this is a real simple change to just square root of u du. Now those boundaries, 0 and 3, those apply to the letter y. My integral is not in terms of y anymore. So I have to change those as well. So I have to substitute 0 in to get that lower boundary. And then I have to substitute 3 in to this u equals y plus 1 to get my new boundaries. So my boundaries are now 1 to 4. Now here's the important thing. Now that I have changed those boundaries and they are in terms of u, this problem from here forward is only in terms of u. I don't ever go back to y's. I don't replace my u with y plus 1 at any point in this problem now. That's where it's different from indefinite integrals. So I'm going to rewrite this as the integral from 1 to 4 of u to the 1/2. I'm going to do reverse power rule. Put my reciprocal of that exponent right there. And so now I'm going to evaluate 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2. I did not go back to the 0 and the 3. I did not put the y plus 1 back in. This problem is now 100% in terms of u. So doing to the 3/2, remember the denominators are root. So the square root of 4 is 2. Then 2 cubed is 8. So I have 2/3 times 8. 16/3. 1 to the 3/2 is just 1. So that would give me 2/3 times 1 is 2/3. And so my final answer is 14/3. So the value of this integral is 14/3. Okay? So I want you to pause the video again, and I want you to try the next 3 problems. Since it's not very different, you just got to change those boundaries. I'm not going to walk you through the next 3. I want you to give them a try. And then we'll come back in a minute and check our answers. All right, so my final answer to B was -1/2. I chose my u to be tangent of x, which made du secant squared x dx. So that was a real easy change to just u du inside of my integral. But I also had to change my boundaries by substituting them into tangent of x. So my new boundaries became -1 to 0, integrated, substitute top minus bottom, and you end up with -1/2 there. Then on C, I chose, there was only one thing in C, but it was in the denominator. So I chose that as my u, x plus 2, which just made du equal to dx. Changed my boundaries as well by substituting into x plus 2. So I ended up with the integral from 2 to 9 of 1 over u du. 1 over u integrates back to natural log of u, evaluated from 2 to 9. Now here's where you get to use your properties of logs. When you substitute in, you get natural log of 9 minus natural log of 2. Now, if this was an FRQ, this is 100% acceptable as an answer. They would take that. This, though, would probably be the multiple choice answer. If you have 2 logarithms that are separated by subtraction, you can merge them together into a single logarithm by dividing the 9 and the 2 like that. So they might write it as 4.5, but they probably will leave it as a 9/2 like that. And then lastly for D, something similar occurs on D there. You can make your u be x squared plus 1. So 1/2 du would be x dx. Your boundaries get changed to 2 to 10. And then you have the integral from 2 to 10 of 1/2 times 1 over u du. So that again becomes natural log of the absolute value of u. That's a very popular u substitution integration. So we end up with 1/2 natural log of 10 minus 1/2 natural log of 2. Totally acceptable as an FRQ. But you could, since they both have 1/2 in front of them, you could combine them by dividing again. 10 divided by 2 would give you 5. So that also would be acceptable as an FRQ answer. It might potentially be a multiple choice answer as well. Another property of logs is that if you have a coefficient in front, that's the same as an exponent on what's inside of the log. So natural log of 5 to the 1/2, or natural log of the square root of 5.